Hey there, welcome back to ECE 382. Today we're going to go into Module 3, the ARM Cortex M, which is the processor on the MSP 432. This is a two-part video. The first part looking at the assembly coding language that we'll do prior to Lesson 3, and the second part will be due prior to Lesson 5, and we'll talk about the architecture of the processor. This first video should prepare you to code in assembly and accomplish the lab for Module 3, the first lab. So let's just jump right in. The Cortex M4 supports something called Thumb Instruction Set Architecture, which is a portion of assembly. It has 205 instructions. The name's not that important, but what's important to know is that this is a subset of all assembly. So this is going to be ARM based. And so this is going to be different than what you saw in 281, which was MIPS. So this is ARM. And we're going to go over what all of the syntax looks like, all the different commands, and get you familiar with that instruction set. The actual everything that all the instructions that the MSP 432 uses, or the Cortex M4, are located in the datasheets folder in your starter code. So if you're looking for that spmu159 alpha.pdf, that's going to provide you everything you need for ARM assembly. So there's the syntax, which includes the label. So that's for looping, etc., or processes, anything like that. The opcode, which is the actual command, move, branch, etc. The operands, and then the comment. There are a few specific things to note. So for example, you have alternate forms of the operand, which is enclosed by angle brackets. Optional operands are enclosed by squiggly braces. And then you have flexible operands, which are op2. So anything you look in documentation and you see something with angle brackets, squiggly braces, that's what those mean, and that should help you to understand what those are doing. So the first thing I want to talk about are some special things that are unique to Code Composer Studio. These are called assembler directives, and they typically go throughout the code, either before or after the actual data, and allow us to kind of create different commands within assembly that's unique to Code Composer Studio and what we'll use for the MSP 432 on the robot. .text, .data, these allow you to kind of differentiate where the following information is stored. The global name allows you to import different function names between functions or between files, so you can kind of use includes and stuff like that. You start a assembly function and end an assembly function with the .asm.end, and then aligning. Don't worry too much about that. I think I take care of most of that for you guys. You end the file with the .end, and then you have these four different types of basically kind of think of them as constants or variables. And we're going to go through examples through the lab of how to use all of these, but I wanted this kind of piece of information here for you so that you can kind of have an idea of, hey, I want to build this, whether it's a constant or a variable, here's how you do it. So we will take a look at those during the lab, but here's the information for you. All right, so let's get into some of the specifics of the coding language. So a lot of what we do in assembly is bitwise logic, and there are a number of times we're going to do this throughout this course, whether it's in assembly or C, this bitwise logic concept. And the reason we're doing this is to kind of to manipulate bits. So we won't talk about that a lot in detail of what that application-wise, but just think of it as ways to kind of manipulate bits. And we'll get into a lot more detail of how to use this. But the four main things we like to do, we want to select a bit, or that's also known as masking a bit. We want to clear a bit, so we want to set it to 0. We want to set a bit, so that means setting it to 1. Or we want to toggle a bit, so if it's a 1, toggling it will change it to 0. If it's 0, toggling it will change to a 1, etc., etc. So we all saw this in 281. There's different ways to do this for each of these different desire. So for selecting and masking a bit, we want to AND it with a 1. And that allows us to select that bit. So for example, if we want to select one of the ports, or maybe one of the input ports on the robot, we can use this AND with 1 to pull the information that's coming from. So the ports are typically in 8 bits. So you have port, so this is say port 1, and it has 8 bits. And those bits correspond to actual hardware, so the actual wires coming off the MSP432. And say 2 of these are connected to bump sensors, and then 6 of those are connected to something else that we don't care about. So we could, if we wanted to see what the input from these 2 bump sensors were, we could AND port 1 bits 0, or all of the port with AND that with 0x03, and that would select these right 2 most bits. And then we would be able to pull that information without all this other stuff we don't actually care about. So that's more, we use selecting for inputs, and then we can also mask things to. So in for an example, let's look at AND R0, R0, and we can throw in, we can do it in hexadecimal. So we can do if we look here at the AND, so this op2 can be either, can be hexadecimal, it can be another register, but let's just do a immediate 0, 0, 1, 1, and that would be, actually, let's just do it in hex. And so that would be the command. So we'd have to get port 1 into R0. We can AND it together, and then now we're saving just the 2 bits right here and here into R0. All right, clear is, we want to set it to 0, so we're going to AND with a 0. So that's just going to be AND R0 with an immediate value of 0. And that's just going to clear that entire register. All right, so OR setting, we use OR with 1. So this is more of like an output. We want to set one of the ports to a 1. We can use OR with 1. So basic idea again, OR R0, R0 with an immediate value of 3. Now bits 0 and 1 are set to 1. And then toggle, as we saw in 281, that's going to be an exclusive OR with 1. And as you can imagine, it's going to be and now we've taken whatever R0 was, so say that's connected to an LED and it was on, we just turned it off. And then we do it again, we're going to turn it on. All right, that's what toggle does, easy. Shift operations, you can use these to manipulate bits, shift them left, shift them right. We remember from 281 potentially that logical and arithmetic shifts do different things, or for shift right. So for arithmetic shift right, it's going to be a shift right is divide by 0. is going to be multiply, or sorry, not divided by 0, divided by 2, multiply by 2. And then a logical shift right, all that is going to do is just kind of shift the bits to the right. And so for the logical shift left, zeros get shifted in here. So we can see here, zeros get shifted in. And for the logical shift right, again, zeros come in here. But for the arithmetic shift, we're going to keep the most significant bit. And that allows us to keep the sign. Remember, sign extended, all those good things. All right, adding and subtraction. So the big thing to note with adding subtraction is the overflow. We want to avoid overflow by all means necessary. And what this means is, if we add two 32-bit registers, we potentially cannot store those in a 32-bit register. So that could cause overflow. So what we need to do is we need to limit overflow as much as possible. And to do that, we have to restrict our input values. Or if we can, do something called promote, perform, check, and then demote. So for example, if we're trying to add, so for this here, if we're trying to add two 8-bit numbers, we want to promote them to 16-bit numbers. Add them, and then check if result can fit in a 16 or in a 8-bit number. And if it does, then we can go back to an 8-bit number. If not, then we have to stay at that 16-bit. And the reason we do this, and you won't have to do this too much in this course, but it allows us to conserve memory and allows us to ensure that there's no overflow. And so when you come and talk about embedded systems and microprocessors, some of those, and like we saw in the last lesson, are very much memory restricted. And so we don't want to store and take up a bunch of memory if we don't actually need it. So you might think, oh, we should just save everything as 32 or 64-bit numbers. And that becomes very time-consuming to process, and then it takes up a lot of memory as well. Same issue with multiplication, just a lot worse, right? Because if we try to multiply two 32-bit numbers, you get a 64-bit number. And again, then we have overflow. But we can, again, perform this promote, check, demote again as well. All right, let's briefly go into the stack. So the stack for this, so the stack is a place to store registers when you're going in and out of functions. So for example, we have these, registers here, R0, R1, R2. If we want to save those, we have to push them onto the stack, do some processing, and then when we return from that function, then we pop them off that stack back into the registers. Now we have those values again. So it's really important to use the stack to conserve our registers and to save that information. And we do that a lot in assembly coding. So the stack is a last in, first out. So you push R0, R1, and R2 onto the stack, and then you're going to be popping the first out, so it'd be reversed. So R2, then R1, and then R0, the contents of those. So you can see here, we push 0, 1, 2, then we're going to pop 2, 1, 0 off. And there's 4 steps to do that. To push, you're going to decrement the stack pointer because the stack pointer builds up. So we start at 2000.ffc, and then we move up to 2000.0000. And so we decrement the stack pointer, because the stack pointer is pointing at the bottom. We go up 1, then we store the value. And then we do the opposite for popping. We start at the top, so we read first, and then we increment the stack pointer to push it back down. There's a few ways to do this. So first off, why does 4 get subtracted and not just 1? The reason 4 because memory, and let's look at this later in the architecture, but because memory is 8-bit addressable, so each piece of memory is only 8 bits, but a register are 32 bits. So these 4 here, that's 4 different memory locations, but that's all R0 because R0 takes all 4 of those because R0 is 32 bits long, and so we need to increment and decrement the stack pointer by 4 so to make space, and then subtract so that we can get back to where we were. So there's different ways to do this. So push R0, R1, R2, that's doing it in 3 different pushes. You can also push something along the lines of this. You can even push your link register, and that's what, when you go into a function, that's your return value, and you can pop the same way. It's all caps though. And that allows you to pop and push at multiple registers at the same time without a whole number of. So what we did here is we jumped into a function, we push our link register, and then we complete the function, and then we pop our link register back into our program counter, so then our program counter properly returns from the function. So now we're kind of talking about function calls. So this is, you can kind of see here some of these directives we were talking about earlier. This is a seed function and a random function. We've stored some variables, address, slope, and offset. And we have, sorry, those are constants, and then we have a variable m up here. So we're going to jump into a lot more of that information in the lab. You're going to learn how to deal with all of that and take a look at all of that. So there's a number of procedure call standards that are important to know with functions. So there's 2 things. Well, actually, there's a lot of things. So if there's 1 input to a function call, it's passed in R0. 2, R0 through R1, 3, R0 through R2, 4, R0 through R3. Then our return value, so these are inputs, and then our return value is in R0. And so you can see here that if our function, when we call our function, we can't use those values because they're the inputs and outputs of the function. And so they have to, sorry, you can use those, but just know that at the end when you return, all that you are returning is R0. And so we have this procedure called standard. It's called the ARM architecture procedure called standard, because you might just be writing a small portion of the code and everyone else might be writing larger portions. And that we have to know where that information is going to be stored and where I should be putting information to go into that function. So all of those are free to use throughout the function call, but functions must preserve values in R4 through R11 in those registers. So you have to save and restore them using the stack. So for example, if I jump into a function and I want to use R4 through R11, I have to save those into, or push those onto the stack, do all my processing, and then pop them on the stack before I return R0. And that allows whoever, the calling function, say this, the main function, knows that R4 through R11 will always be safe. If I have values in R4, I call a function, those values will still be in R4 after the function call. But it can modify R0 through R3 and R12 freely. So that on the flip side, then, if I'm the main function, I can't assume R0 through R3 or R12 will be the same after a function call. And so this really goes into memory management design. How do I design my code so I can properly use the functions? And we'll see all of this in the first lab. There is all of these procedure call standards are written up in the lab so you can see them again. So those are key. So the link register is how we know where to return to after the program after the function is called. So that's the return address basically. And so that must be set every time before you go into a function call so that then we know where to go back to when we need to. The link register is automatically set when a branch and link call is made. But there are times where we might have to set the link register ourselves. So if a function calls another function though, we have to preserve LR. And that's because that so we have main calls a function, the link register is set so we know where to go back in main. If that function then calls another function, it's going to set the link register potentially, well, it will overwrite that original link register. And then now once we finish that second sub function, we try to return to main. Now we have no clue where we are. So that's why we have to make sure we are maintaining and preserving the link register value. So whenever a function is called, two things happen. We need to set link register and we need to set the PC, the program counter, to the function address. And if you're not familiar with what the program counter is, that's where in memory, as we are stepping through each instruction, the program counter is pointing to the current instruction that is running. And then the link register is going to save that information, save the return function, the return address so we can return from the function. And the value we use, the instruction to return is either branch branch linked register. So that's going to branch to the address that our return address is. All right, so functions are pretty complex in assembly. We'll see a lot of examples. We're going to work through some of this in the pre-lab and in the lab, and so you can kind of learn a little bit more of what these registers do and how they are used. Conditionals are also complex. All right, so the way a conditional works is you can think of it as 3 steps. So first off, you're going to bring a value into a register. So we're going to load something into a register. So we can see here we're going to load the address G2, which is this variable here. Sorry, G2. So we're going to load a variable G1 and G2 into R2 and R1. We're going to compare those, R1 and R2, and depending on what that result is of that compare, so the compare is going to set a number of flags. Here are a number of flags. Right, these flags are your current program status registers. The main ones we'll focus on N, which is the negative condition, Z, 0 condition, Z, C is your carry condition, V is overflow, and those are the main ones that we are concerned with. So you can imagine that if we compare 2 values, so the compare basically just subtracts them from each other, and then depending on what happens, it's going to set these flags. So compare is going to check G1 and G2. If there is, if Z equals 1, that means that the result of that negative or that subtraction was 0, then they're equal. If 0 is not 0, Z equals not 0, then it's not equal, obviously. If it is 0 and then there is a negative flag and overflow, and then that means we are going to have a greater than. So there's going to, so the R2 is going to be greater than R1. So that's what all these different flags and how they relate to the compare. There are different functions. So not only can you use compare, but there's different functions, operands that allow us to set those flags. So the compare is 1, add S, sub S, and multiply S. So any of these 3, you could replace that compare, do those, and then branch depending on what happens. So that would be very similar to using the compare, but allows us to kind of be a little bit more fluid and not just use a compare every time. So looking at while loops and for loops, here are 2 examples of how to use while loops and for loops in assembly. So typically you will do something and then compare and then branch back to that loop. So you can see here we're going to compare and we're going to loop until these 2 are equal or greater than or whatever. So this one is branch less than. And so we are branching when when G2 is less than G1, and then we'll branch down to done, and we'll continue through. So you can see in this little flow chart, the basic idea is while G2 is greater than G1, we're going to continue looping. So we're going back to this branch loop, branch loop, branch loop, and then once the G2 is less than or equal to G1, then we'll branch to done and complete that. Same idea for for loops, except you'll probably be doing something to a counter. So that counter is getting decremented by 1 here. You can see that I equals 10. While I is not equal to 0, decrement, and then complete the body. And we'll do that again until this is equal to 0, and then we'll branch down to done. The last kind of topic to look at is memory access instructions. And then I have a few examples that will help out with the lab or anything along those lines down the road with assembly. So these are the different types of load and store. So you can store up to, so this type we can replace with either nothing, leave it blank, then it's a word. You can do a byte. You can store a signed byte, unsigned half word, signed half word, or 64-bit data. And so what that allows us to do is if we want just a byte of data to get stored into memory, we can use a store byte instead of the whole 32 bits because we don't know exactly what those 32 bits would do, and we might overwrite some stuff. So if we only want to store a byte, then use the B type, and then so on and so forth. So these few examples, so these allow us to set a constant. So here we're using that .word directive. So pi, we're going to store the value 314159. You can see here we're not using a float. Floats are very difficult to work with in assembly. So we're going to just use this word, and we're going to deal with that. We're going to load that value into R6. And so once that command is completed, R6 will hold the value 314159. We can do different variables. So this is basically an array with 4 different values, 2000, 2733, so on and so forth. And this is a pointer to that array. And so we can store input's address into R10, which is going to be pointing to this array of longs. And then as we loop through here, potentially each time we loop, then we're going to grab the first value, which is going to be stored there. And then the next time through, we're going to grab the next one, and next one. So you'll use both of these examples in the lab and pre-lab. So these are just kind of to help you kind of understand what's going on. And last but not least is if we are trying to work with the input-output on the MSP432, we'll do this again in like module 6 or 7. So you don't have to worry about it too much, but it's just good to know, I think it's during the GPIO lab, that this is here for you to take a look at. So if we want to turn on an LED that's located at pin 5-4, so that's the header 5, and then pin 4 of that header, or port 5, and then pin 4 of that port. Then we will take this, which would represent that memory address of that port. We load that into memory, so R1 now is a pointer. We read 8 bits out of it because each of these ports is only a bit. Or sorry, each of these ports is 8 bits, so you know port 50 through port 57. So that port has 7 different pins, or sorry, 8 pins, and so we will load in that whole byte. We'll read that information. We will set, or remember sets one of the bits, and then we'll store all that information back into this port. So what we're doing here is we're only changing bit 4. So we load the whole byte into our register. We change 1 bit using OR, and then we store it all back on that port, and we'll turn on that LED. We could, if we want to toggle the LED, instead of using an OR there, we'd use the exclusive OR. That just kind of allows us to then use assembly to turn on or turn off an LED, which we will do later. That's it for this portion of the video. Next time, like I said, we're going to go into the architecture, but this is enough to get you ready for the lab and to do the pre-lab.